Okay, I hope my screen is visible to all of you. Hello, can anyone confirm?
Yes, sir.
Okay.
Yes, sir.
Uh, Welcome to the 12th tutorial of materials characterization code. I am Sabyasachi Panda from Department of Metallurgical Materials Engineering. So in the last class actually we stopped at we discussed about the bright field and dark field imaging, and as well as there is different type of dark field imaging, that is called center dark field, and also we saw how the selected area electron diffraction are obtained, as well as what are the differences between SAED, that means selected area electron diffraction, and CBED, that is convergent beam electron diffraction. That is one mode we are using specifically in SAED mode we are using parallel beam to illuminate our sample and or to interact with our sample, and in CBD we use a convergent beam to interact our sample and get the images. We stopped there, but our ultimate focus is to get the image and get the diffraction pattern, and to extract information from them. And since from the very beginning of TM, we have always maintained this relationship, is that TM images are 2D projection of three-dimensional images. So it is an also TM gives an averaged image of the three-dimensional object, right? Ultimately, all of these images and the features associated with the images are um, to be interpreted. That means we are getting some two-dimensional images which are to be interpreted in such a manner that we have to see what kind of features are there in our material, and if there are any additional additional features are there which are not expected in the material, then what are those kind of features, or from which regions those features are coming. That means ultimately we have to if we want to interpret our image so that we can get the correct information from our material, then we have to uh, know the contrast mechanisms in our image. Because the in the bright field as well as the dark field imaging also, there are we are interpreting our messages based on the contrast that we are getting. In bright field image, the background is bright and the sample is dark, and similarly in the dark field image, the background is dark and the sample is bright. So due to those contrast mechanism, so we can see that there is a difference in the contrast. Those kind of difference when we are going to see, then we have to know the contrast mechanism so that we will be correctly interpret the image. And why we have to see the contrast mechanism? First of all, what do you mean by contrast? If I say, then contrast is nothing but the difference in intensity, and ultimately whatever we are when we are interacting our specimen with the incident electron beam, we want to see the intensity, like in which region from our sample the intensity is varying. So it is nothing but the difference in intensity between two adjacent areas. So if I am taking a specific region, then and I am dividing this sample into region 1 and region 2, then what is the difference in intensity coming from region 1 as well as what is region 1 and region 2? So those intensity I will be if I am able to quantify in some manner that this is the value of the intensity between these two regions I have taken, but there might be some new a number of regions also in your sample. So when these kind of intensity variation we want to quantify, then we go for the contrast variation. So contrast is nothing but the difference in intensity. So we have known that contrast is nothing but the if we want to numerically quantify it, then delta I by I, where the delta I refers to the difference in the intensity between our two desired regions, and I is the intensity of the original region. Okay, so this is what the formula for the contrast. Ideally, we say that the contrast should be greater than 10%. Theoretical limit is that if the contrast value will be greater than 5%, then we will be able to interpret our image that whether the contrast is strong or the contrast is weak. But this is a theoretical value, but to interpret correctly in a TEM image, we generally prefer that our contrast value should be greater than 10%, so that we will be able to see that whether that contrast is coming due to the phase, whether that contrast is coming due to some interaction or the diffraction or scattering, that phenomena that are taking place inside the material. So contrast is nothing but the ratio between two intensity. So that is why contrast is a unitless value. Okay, and this contrast, why these contrasts are coming in our material, in our image when we are taking the image, that we have to see. And the difference in intensity, that's what we observed at the contrast. But why this difference in intensity is coming? Because we have our incident beam is made up of electron, and if we are talking about if we are saying that electron is showing its wave nature, then the electron wave can change both its amplitude as well as phase, right? So these two phenomena can take place when an electron beam, incident electron beam, interacts with your specimen. So it can change after interaction with the specimen, the amplitude will be changed, as well as the phase will also change as it goes through the specimen. So depending on its variation in amplitude, depending on its variation in phase, so that is why the intensity will change. And the moment intensity changes from a particular region of your sample, contrast will be there, because here once the intensity changes, it will be reflecting in your contrast, and that is why we have to study the contrast mechanism. So another thing I want to mention it here, generally people get confused with contrast and intensity. Remember, those two are two completely different terms. So intensity, the ratio of the difference in intensity to the original intensity, that will give you the contrast. Okay, intensity is nothing but the if we are talking about that I have a detector with me, intensity is how many number of electrons I am collecting. Let's say this is my detector, this is my detector here. Then after the interaction with my specimen, then this is the incident beam, then how many, let's say these sum of the electrons are there, then how many electrons I am able to collect per area. So that defines my intensity. Okay, so this is what my intensity is. But my contrast is in a specific area, what are the ratio of those intensity. So if in region 1 I am getting, let's say 50, so here what are the particles that I will be my detector will be collecting? Let's say electrons will be eventually collected by my detector. Okay, let's say in region 1 my detector collects 50 electron, in region 2 my detector collects 38 electrons. So then I can see that though the intensity is varying here, but since the intensity is varying, that is why I will be able to get a contrast in my material. So that is why do not get confused with contrast and intensity, because intensity is how many number of atoms or how many number of electrons your detector is detecting per unit area, right? And contrast is the ratio of the intensity. And when we talk about a good contrast or I can say, and there are two terminology associated with contrast and intensity, to different pair of terminology. Always remember, when we talk in terms of contrast, we say two things. One is either strong contrast or we can say weak contrast, right? However, when we are talking about intensity we talk about it is a bright intensity or a dark intensity. Okay, so when we talk about the contrast we always talk in terms of whether the contrast, we never say that the contrast is bright contrast, the contrast is a dark contrast. No, the intensity will be bright or the intensity will be dark. However, the contrast always refers to either a strong contrast or a weak contrast. Now coming to this strong contrast or weak contrast, so we always prefer the strong contrast, this value in our strong contrast in our image. Why? Because only then we will be able to interpret that what are the different features are there in our sample. So to get a strong contrast, what we do, what is desired to get a strong contrast, it is always remember, it is desired that our the detector should detect always low intensity. Okay, so when we are getting low intensity, then only we will be able to get a strong contrast. When we are getting a high intensity, then in that case we will not be able to get a good contrast. However, remember, though I am saying that the strong contrast, there are two different types of now that we are talking about contrast mechanism. So due to which phenomena that our contrast we can see in our images, one will be due to amplitude variation, another one will be due to phase variation. Like, because we are here we are seeing that the electron wave, as it traverses through the specimen, it can change both amplitude and phase. So that is why two types of contrast mechanism we can see. One will be amplitude contrast, another one will be phase contrast. Now coming back to this strong contrast and weak contrast. So to get a strong contrast, it is desired that our intensity should be as low as possible. To get a weak contrast, the intensity should be high. And but the interesting thing here is, once your intensity will be low, to get a, let's say in this case, in the case of A, once your intensity will be low, you are getting a strong contrast. However, the image will not be the resolution of your image will be very poor. Why? Because you will not be able to capture all the electrons that have interacted with your specimen. To get a low contrast, you need high intensity. Here, once you get the high intensity, that means after interacting with your specimen, here many number of electrons which have interacted with your specimen, they are getting captured by your detector. So you will be getting a good resolution of your image, less noise. So you will be getting, you will be able to see that what are the different types of features are there in your material. However, your contrast will be in that case poor. So it is always desired to have an optimum balance between intensity as well as contrast. So we should not go to extremely low intensity such that our contrast will be strong, but in that case noise will be high and our image resolution will be low. Similarly, we should not go to the maximum to collect the maximum intensity. In that case, what will happen? Because the contrast will be in that case low. So that is why when collecting, when we have to select the, either we are going for strong contrast or the weak contrast, we put the aperture into place. So based on the aperture, we select that how many number of electrons or which electrons, whether it's a bright electron or whether it's low angle scattered electron or whether it's a high angle elastically scattered electrons we want to collect. So based on those things, we will see subsequently how the contrast mechanism varies. So now coming to the first type of contrast. So this is the amplitude contrast. Why amplitude contrast come? Because there are, when electron wave goes through your specimen, and remember the specimen is already less than 100 nanometer thin, because that is the penetration power of an electron. So if we make the electron our specimen greater than 100 nanometer, then the electron cannot penetrate and we will not be able to get the transmitted electron. So when our sample is that much thin, then why there will be amplitude change first of all, and if there is amplitude change, then only the amplitude contrast will come. So coming to this amplitude contrast is actually two types of amplitude contrast are there. One will be the mass thickness contrast, another one will be the diffraction contrast. So due to these two reasons, the amplitude of the electron wave which interacts with your sample varies, and that is why we are getting contrast. So what do you mean by mass thickness contrast? So mass thickness contrast results from variation in or mass or thickness of or a combination of two. So either of these combination if happens, then the contrast mechanism changes, and finally we will be able to get the intensity accordingly. So how this thing happens, how the mass thickness, how it plays a role into the intensity or the beams or the electrons that are captured by the detector. Let's see. Okay, and we will see that how due to the variation in mass or thickness, so that is why this contrast is called as mass thickness contrast. And there is another type of contrast is that is known as the diffraction contrast. So diffraction contrast, why? Because the diffraction can vary locally, because the specimen is not perfect. Unless no matter how much thinning we do, we will never be able to obtain a perfectly flat specimen. So even within let's say in the order of this is the let's say this is my T I am talking about, this is the T, and T will be in the order of let's say 5 nanometer to somewhere 50 nanometer. So even in this thickness, if there are variation in the order of nanometer, then also the diffraction. Why there will be if there is a variation in the order of nanometer? Because your electron wave will interact with more number of atoms, will interact with more number of planes where there will be subsequently atoms will be placed. So due to those interaction, so that is why in those planes also where the atoms are situated, the diffraction can take place. So let's say one electron is coming within the coming out of the specimen where 4 layer of atoms are there. Another electron is coming out of the specimen after interacting 10 layers of atoms, right? So though in case of layer of atom is 6, so difference is 6. However, for an electron beam, when we are talking about an electron wave, this 6 layer of interaction will also affect its amplitude, right? So that is why the diffraction contrast happen, because the diffraction can also vary locally, and specimen will never be flat until and unless the closest to a flat specimen we can go is a method called FIB, but still it is not an also ideal situation. This FIB is known as focused ion beam. Okay, so this focused ion beam, we can go as close to as flat that we can make of a sample, but still there will be some local variation, and due to those local variation, the diffraction will take place, and which will once the diffraction is taking place, then the amplitude will also vary, right? And here this is an example of diffraction contrast. So here we can see you can see that there are lots of diffracted point at there. Point A, if you look at, so here in this point A, this is the direct beam or the transmitted beam which has gone undeviated, and this is the another diffracted spot, the B, and these two are the strongest spot that we can see. However, these two are not the only two spots in a diffraction pattern. So this is a diffraction pattern, and here if we see, there are also other diffracted spots are also there. Here, all these spots are also, you can see these spots, you can see. So they are also some diffracted spot. They are associated with lattice plate. So to see the diffraction contrast, we have to, so this condition we will see in the later slide. This condition is known as two beam condition. Why we need a two beam condition, we will see. Okay, to see a diffraction contrast, we can see that we have to go to a two beam condition in case of to categorize the dynamical to see to observe the dynamical the dynamic diffraction contrast. So this is a mass, so the amplitude contrast, that means the amplitude of the electrons which have already interacted with our specimen, those will vary due to one will be either from the mass or from the thickness or from the both, or then the diffraction takes place, right? And here you can see in the left side this image, from this image, as you can see, let's say the incident electron beam with uniform intensity is coming, right? However, if the incident electron beam with uniform intensity is coming and after interacting with the specimen, the image, you can see that there is variation in the, here the intensity is high, here the intensity will be low, right? So since these kind of intensity peaks and troughs will be there, intensity variation will be there, so that is why we always get some intensity variation throughout our image, which will eventually gives us the contrast mechanism, right? And okay, here we have discussed about means we have introduced a concept of two beam condition. However, I want to let's say go to this mass thickness contrast. So the mass thickness contrast, I will just give you an introduction, because in the later slides we will see the mass thickness contrast. Let's assume that we are collecting only as of now, we consider that we are only collecting the bright field image. Bright field image means we are only collecting the image which are coming through the optic axis, right? So if we are saying that thing, let's say this is my material, yeah, this will be my material, and my incident beam is coming, let's say this is, and 50 number of electrons are there in my incident beam. Here also same 50 number of electrons are coming. Remember, this slope variation is means we cannot make this slope perfectly flat, right? Because it is in the order of nanometer, and so there are let's the thickness is in the order of nanometer, which is very difficult to remove. So after the TM sample preparation, here also 50 electrons are coming. However, since the thickness here at this point, let's say 0.1 and this is 0.2, right? So since after interacting with the, and if I'm saying that this is my specimen, then after interacting with this all this set of planes, here let's say I am getting 47 number of electrons, right? However, at point 2, if I am interacting with all these since the thickness is larger, let's say I am getting 43 number of electrons in my detector. That means 7 electrons, let's say 7 electrons are going away. Why they are going away? Because of the thickness variation in this sample, right? Let's say in a special case, if I do let's say another case, 50 electrons are coming. However, in this part of the material, the mass is so heavy, okay? So it is so heavy that this mass is different from this mass, okay? So this mass is heavy. So what will happen when the heavier mass, when the electron beam interacts with the heavier mass? So they will also scatter more. Since they will be scattering more, instead of here 43, now I will be getting, let's say 32 number of electrons, because 18 electrons will be scattered more, and my detector is not able to capture all these things, because I am currently considering that I am collecting all the I am taking my image in a bright field format. So since these you can see, either if we are changing the thickness, then the number of electrons that my detector is able to collect is varying. Let's say same material, but since the thickness I am varying, then some more scattering will happen due to the extra thickness, and my number of electrons that I am getting at my detector will be varying. Here I am getting 47 number of electrons. Here my detector can detect 43 number of electrons. So and in the case where my material is also embedded with a heavy metal or heavy element, then I am getting my detector will be only able to detect 32 number of electrons. That means if I am projecting this entire three-dimensional material into a two-dimensional image, then in some places my image will be brighter. Where my image will be brighter? Where I am getting this 47 number of image, 47, where my detector is able to detect this 47 number of electron. Then in some places what will happen, my image will be a little bit less bright. That means where my detector is able to detect 43 number of electron, and in some cases my image will be means the least bright, or where my image my detector will be able to get or collect 32 number of electrons. So this is how my intensity variation, since here I am getting more intensity, here I am getting middle intensity, and here I am getting the least number of intensity. Since the intensity variation will be there due to the thickness or the mass variation in my sample, then in that case the intensity variation will be eventually leading to contrast. So that is why there are different types of contrast I can see in my samples, and that this type of contrast contrast, when we are seeing that, the contrast is known as mass thickness contrast. That means either thickness varies in my sample or the mass varies in my sample, then I will be able to get the mass thickness contrast. And the diffraction contrast, what is that? The diffraction contrast is when the contrast varies due to the diffraction. We will see how the due to diffraction the contrast varies. Then we'll see there are two different types of contrast mechanism in diffraction contrast itself. So one will be associated with kinematical contrast, another one will be associated with dynamical contrast. So now let's see. So remember, so what are the two different types of contrast mechanism? One will be amplitude contrast, another one will be phase contrast. In amplitude contrast itself there are two different types of contrast. One will be mass thickness contrast, another one will be diffraction contrast. Now coming to the bright field and dark field images, if we are going to see the bright field and dark field image here, bright field means the background will be bright and the sample will be dark, and the dark field image means my background will be dark and the sample will be bright, right? So this kind of imaging if we want to see, then there is an advanced method of TEM, that is called scanning transmission electron microscopy. So how the thing is to get any kind of contrast mechanism, we require to collect we require the intensity. So how much intensity, or effectively how much electron, how much direct beam electron, how much scattered beam electron we want to collect, that only will define eventually that what are the different type of contrast are there. So let's say I am talking in terms of TM and STM. So TM is transmission electron microscopy, STM is scanning transmission electron microscopy. So in STM what we do, we select either the direct electron, direct beam, or the scattered beam. So what are the two these are the two different modes of obtaining our contrast, or to see how much contrast our sample is able to give. So in TM what we do, how we are able to get the different intensity from different regions. So what we do, we insert a objective diaphragm. Is this diaphragm means nothing, this is an objective aperture, right? So the job of objective aperture we saw in the last class. The job of aperture is to give us the required or the desired beams, and to stop the unwanted or the undesired beams. So that's what the job of this objective diaphragm or the objective aperture. So to get a particular number of a particular intensity from a particular region, if we want to, let's say I want to collect all the direct beam, then my aperture will be in a place such that all the direct beams will only be collected by my detector, or by my detector. If I want to collect the diffracted beam only and stop all the direct beam, then my aperture will be placed in such a way that all the diffracted beam will be collected by the detector. So this is the mode of operation how we can collect different intensity or different signals from by using objective aperture to get different type of contrast. Okay, so this is the bright field. So in TM we know that this is how we collect the bright field and dark field image. However, in STM, that means scanning transmission electron microscopy, instead of putting an objective aperture, what we do, we do not insert any kind of objective aperture, rather we do a we play with the detector system itself. Here the detector is fixed and we are only changing the objective aperture position. In STM, however, to collect a bright field or the dark field image, because eventually bright field and dark field image, we will be able to see the contrast. So to get a bright field and dark field image in STM, in both the cases, what we do, we change the position of the we change the detector itself. So if we want to let's say this is the first case in the STEM, case number C. If we want to collect all the bright field electrons from our which have interacted with our sample and block all the give away all the diffracted electron. So what we do, we put a bright field detector here. That means bright field detector means the direct beams which is coming and interacting with our specimen. So that is what we do for a STEM bright field image. And if we were to do the STEM bright field image, then in that case the we will be getting the bright field means the background will be bright and our sample will be dark. Similarly, if we want to say, let's say I want to see the dark field imaging in STEM. So dark field imaging means we want to get the diffracted rays which have interacted with our specimen, and depending on their Bragg's condition or the diffraction condition, they have been scattered or they have been diffracted, and we want to see what are the orientation of the planes are there in my material. So if we want to calculate those, if we want to see in our image that what are the diffracted plane or what are the planes, a particular set of planes that are present in my material, then what we do, we insert the dark field detector. And this dark field detector we insert in such a way that it is a, so let's say this is my detector and this total is, this is my detector. Okay, and what I will do, let's say this is my electron beam that is coming out of this plane or going into the plane. So my electron beam which will be diffracted at an angle, at a higher angle, then they will only be collected by this detector. So since this is an it's an annular kind of shape, so that is why this is known as ADF, that means annular dark field detector. Okay, so TM, what we do in TM, we TM play with the aperture to obtain a bright field or dark field image so that we can interpret our image. In STM, however, we do not insert the aperture, rather we play with our detector. So if we want to get a bright field image, we insert the bright field detector. If we want to get the dark field image, then we insert the ADF for the annular dark field image, annular dark field detector, right? Now, so coming to the mass thickness contrast, we have seen how the mass thickness contrast eventually gives us the contrast mechanism, because due to the variation in thickness, the number of beams that are going to be collected in our detector system will be varying, because thickness means varying thickness means our electron, even if the same number of electrons are coming and interacting with our specimen, however after the interaction, the number of electrons with same property will be those numbers will be varying. So that is why the mass thickness contrast comes. So this mass thickness contrast arises from incoherent scattering, incoherent elastic scattering. So this scattering is known as also Rutherford scattering of electrons. Okay, so this mass thickness contrast arises from the incoherent scattering of electrons, and the image which has been formed with electrons scattered at low angle, those electron only mass thickness contrast dominates. Okay, however we know that from n lambda is equal to 2d sine theta. So here this is the condition for diffraction. For low angle, if we can in the last class we have seen that the theta will be almost close to 1 degree. That means so theta we have seen in the last class, I think 0.5 degree or something, when we are talking about some material. So so this theta value will be very less. So since the theta value is very less, when we are talking about electrons scattered at low angles, then the Bragg diffraction will also happen. That means when we are talking about the mass thickness contrast, at that time also the diffraction contrast will be, we will be able to see the diffraction contrast. So that is why that means it competes with the Bragg mass thickness contrast, competes with the diffraction contrast. So whatever contrast we will be able to we are finally will be getting, we cannot completely eliminate this Bragg diffraction contrast, because at low angle those contrast mechanism will also change the amplitude, and the mass thickness contrast mechanism also change the amplitude. So eventually the amplitude variation that we are getting, so those will be even at extreme low angle, this will be due to mass thickness contrast plus diffraction contrast. So we want to minimize this diffraction contrast as much as possible. So how we can minimize this contrast as much as possible? So what we do, at this stage we will assume that no whatever contrast is there, the diffraction, the no contribution to the image from diffraction contrast. How? Since we know that at low angle the Bragg diffraction contrast varies, or the Bragg diffraction contrast also is a dominant mechanism. So this mass thickness contrast we generally see to see the contrast mechanism. With this mass thickness contrast mechanism we apply to see the contrast mechanism in non-crystalline materials. Why? And non-crystalline materials like polymer, like biological samples. Why? Since polymer, non-crystalline, that means amorphous or semi-crystalline material, they will not be able to, in those materials the diffraction will be very less. If I am talking about an amorphous material, then the diffraction will be there will be no diffraction. If I am talking about a semi-crystalline material, then there will be very weak diffraction will be taking place. So since those diffraction, in that case whatever amplitude difference we will be getting, in that case it will be predominantly the mass thickness contrast. So this contrast mechanism is predominantly used to see the different features in non-crystalline materials like polymer and biological samples, right? And this is the mechanism behind the mass thickness contrast. As you can see, the incident beam is coming, and this is one type of specimen where I have lower mass thickness. Lower mass thickness means I am talking about, let's say, lower atomic masses are there in my material, and in this right side of this my specimen there will be higher atomic mass materials are there. So since the higher atomic mass specimen are there, even with a now in this figure I am assuming that constant T, that means constant thickness. In earlier case when I showed you the mass thickness contrast, there I have assumed that in the first set that variable T, that means variable thickness, how variable thickness will give rise to variable intensity and eventually variable contrast. Now in this case what we have done, we have kept our constant same, that means same T I have kept. However, since the lower mass and higher mass in two different region, I am talking about in the left side as well as from the right side. So since lower mass thickness is there, so it will not be able to scatter more electrons. That means more and more electrons will be coming straight, and with the help of objective lens and objective aperture we will be able to get more intensity on this side. So that is why you can see the intensity is high on this side, okay, because I am more and more number of electrons are not getting scattered, and rather they are getting focused here by objective aperture, they are getting focused in image plane. So here you can see high intensity in this side, okay. Now coming to the higher mass thickness, higher mass means they are able to scatter more to the incident electron beam. So since their scattering is more, but I am taking here, I am taking a bright field image. So since I am taking a bright field image and the scattering is more, then all my scattered wave from here to here, all my scattered beams, they are blocked by objective aperture. So in that case, whatever the intensity I will be getting here, due to since more number of electrons are getting scattered and less number of electrons are coming through my objective aperture, so here in this side I will be getting low intensity. So even with a same constant thickness scenario, if I am varying the mass, So varying the mass in a specimen, then I will be getting in one side I will be getting higher intensity, in another side I will be getting lower intensity. Since there will be variation in intensity, I will be definitely getting contrast, right? So this is what I have written it here. In case of a bright field, thicker or higher mass areas will appear darker. Why it will appear darker? Because they will be having low intensity. That means less number of electrons will be focused to create the image in the image plane. So, and lower mass areas will be appear brighter, okay, in a bright field image. So then we have to see that which are the TM variables. If I am putting my sample for a to see an to observe a mass thickness contrast, then what are the variables that affect this mass thickness contrast? One is objective aperture size, another one will be the KV. That means my accelerating potential. If my accelerating potential will be high, then in that case what will happen? More and more number of electrons will be collected, right? More means my accelerating potential will be high, means even if I have a higher mass thickness, then my intensity will be even if more number of electrons are scattered in this direction, some electrons will also be coming and they will be focused here, right? And if my higher KV, that means if I am saying higher KV, then here I will also get let's say instead of one electron beam contributing to my image, I will get two electron beam contributing to my image, right? Higher KV means, and in this case also I will be getting, let's say, 4 electron beam contributing to my image. So that means higher KV means higher average intensity. Average intensity I am saying in the sense that the let's say in this side I am collecting 15 number of electron beam, in this side I am collecting 10 number of electron beam. So the average is somewhere 10 plus 15 by 2, let's say 12.5 I am talking. I am giving some random numerical values, okay? So higher KV means that. If I am giving a lower KV, right? So if I am giving a lower KV, then in that case what will happen? Lower average intensity. So lower average intensity means my intensity will be lower, and in the contrast mechanism from the first slide, what we have studied, that lower intensity will be giving you a better contrast, right? So in this case what will happen? Lower average intensity means I will be getting contrast, the variation in the higher mass thickness and the variation in the lower mass thickness electron beam will be large, and in that case my contrast mechanism will be higher. So it is always desired that a lower KV is required to obtain a good mass thickness contrast. Similar case also is applicable for objective aperture size. Objective aperture size means if we are increasing our objective aperture, that means we are allowing more number of beams, whether it is diffracted beam or whether it is direct beam, to get collected in the image plane. Let's say here it is an image plane. If we are restricting our objective aperture size to a very small value, then we are also, in that case what will happen? If we are opening the objective aperture, that means making our objective aperture bigger, then the average intensity will be high. Then when the average intensity will be high, there the contrast will be poor. That means when we are to counter that, when we are reducing the objective aperture size, then we are collecting less number of electrons. When we are collecting less number of electrons, only the electrons which are coming, either the direct electrons or the electrons which are getting focused from the lower mass thickness area, those will be collected, right? And that is how we will be getting a lower average intensity in the image. And once we get the lower average intensity in the image, our contrast will also be very good. So that is what the TM variables. If we want to image a polymer sample or a non-crystalline sample and we want to see the mass thickness contrast, then either we have to reduce the this accelerating potential, accelerating voltage, or the objective aperture size. Remember, once we reduce the objective aperture size, then what will happen? The image resolution will also come down. Why? Because in the then you are not collecting the all the beams which are coming after interaction with your sample. And this is an example of, so here the objective aperture size is 70 micron, here the objective aperture size is 10 micron. right? So here you can see better contrast in the 10 micron. You can see better contrast. Why? Because the objective aperture size here is not collecting many beams, whether they are direct beam or the diffracted beam. Okay, so they are not, objective aperture is not collecting the unwanted diffracted beam, rather the image is created by collecting the direct beam. So here you can see some of the features in this region. If you see some of the feature in this region which you are not clearly able to distinguish, in this region you are able to distinguish those features, right? So this is an diagram showing that how the objective aperture size can affect our mass thickness contrast. Now there are two process that we do to interpret correctly our non-crystalline sample. Because this mass thickness contrast, when we are talking about, we are talking that polymer sample, amorphous sample, semi-crystalline samples we are going to image. So there are two techniques which we do generally. One technique is known as shadowing and another technique is known as staining. So what do you mean by shadowing? Shadowing means we always introduce some mass contrast to a thickness contrast image. Let's say due to the thickness variation, and we know that always let's say currently our sample does not have any of the our sample is made up of one type of material. So we do not have a like here in the previous case we have seen higher mass thickness, lower mass thickness. So in our sample currently there is no higher mass thickness or lower mass thickness. Let's say mass thickness is same because our material is same. So in that case in most of the time we will be able to get this thickness contrast. But if we are able to get this thickness contrast, then how do we perceive that? Because eventually it's a three-dimensional image and it will be projected in two dimension, right? So how do we perceive whether the interpretation that we have done is correct or not? So we introduce knowingly, we intentionally introduce one type of contrast that is known as mass contrast. What do we do with the mass contrast? We either some platinum or some gold we put in our sample, right? So when we put all these some spray kind of thing, some small powder particles, when we put on our sample, then due to those mass contrast which has been introduced to already which has been the thickness contrast, then we can clearly see the image, and the result of that you can see from the left side of the figure. So this is an image which we have collected, and here though we can see that these are the grain, we can see in this image clearly that there are grain boundaries are there, and some structures are there, because here there are two types of color you can see. One will be white, and here in this image we can see some areas are bright or and some areas are dark. That's what I can say. But whether it is a completely flat specimen or not, that we cannot say from simply from looking at this image. So this is the reason what we do, we intentionally we put some heavy metal or heavy element into this polymeric sample, that is to introduce a mass contrast. So this is my thickness contrast initially that I was getting. So this was my thickness contrast. Due to variation in my thickness, I was getting some bright areas like this, and due to thickness and also I was getting some dark areas. Let's say one of the dark area is this one. Okay, I was getting this thing. However, after doing the shadowing, that means intentionally if I introduce some heavy element like AU or PT, then I can see clearly I'll be getting, after here I can write, after introducing mass contrast. After introducing mass contrast, you can see the difference between the image number 1 and image number 2. Here you can clearly see that this is a fracture surface, and fracture surface means some of the grains are broken, some are lying on top of each other. However, in the image number 1 we are not able to distinguish those features correctly. So this is one of the techniques that we do to our polymeric sample to clearly interpret the contrast that we are getting, and clearly interpret the image also. Now, this is shadowing is one of the techniques. Another technique is for biological sample. So in biological sample, what we do the staining process, right? So staining means nothing but with in biological sample there are typical heavy metals, also similar heavy metals we introduce to our material. Those material are osmium, lead and uranium. So these are the typical heavy metals that we introduce into our material. And here what will happen, you can see now these are the some of the dark regions. Okay, so since these are the dark region, these dark region actually in biological sample, so there will be some bonds will be there, carbon, hydrogen and so carbon bonds will be there, carbon hydrogen bonds will be there. So those bonds will be we can see completely once we introduce this Pb, U and OS, or these three, any of these three metal if we introduce, so that process is known as staining. And here this darker region are eventually suggesting us that these region belong to the unsaturated bonds. Okay, so that is how we will be able to, after doing the staining process, before doing the staining we will not be able to figure out that which region is bright, which region is dark. Then after doing the staining process in biological sample, we will be able to clearly distinguish. Okay, and then comes inside this mass thickness contrast. Remember, there is another type of contrast that is called a Z contrast. So Z means the atomic number contrast is there. Okay, so as Z is not a separate type of contrast, rather it is a variant of we can say the mass thickness contrast. And why I am saying the mass thickness contrast, because the Z contrast is a high resolution imaging technique. Okay, when we want to see some of when we want to see the thickness that has been the contrast that is coming due to mass thickness, and we want to see the we want to go at an extremely high resolution, then we go for this Z contrast. Okay, and this Z contrast actually represents the limit of mass thickness contrast, right? So this shows us the limit of mass thickness contrast. And when since where detectable scattering arises from single atom or column, so that is what this Z contrast means. And this Z contrast is how we can see the contrast due to the inelastic scattering power of atom. So the more inelastic scattering happens, the more number of atoms will be collected. So more number of atoms will be collected in our, let's say, dark field detector, ADF detector, we can collect, and due to those, so we can get the like compositional, we can say it here, the compositional information of a complex structure, we can say that we are able to clearly see. And for to get those information we need this Z contrast. Okay, and here this is an example that and also yes, these Z contrast images are also termed as HDF images. So this HDF is nothing, we have seen the HDF is high angle annular dark field image, right? And last class we have seen what are the bright field, so bright field, dark field, and the difference between ADF and HDF, that means HADF. So here we in this image you can see, if our angle, the collection angle of our detector is less than 10 millirad. 10 millirad is how much angle? We have talked 10 millirad is 0.5 degree. So if I am talking about 10 millirad, that means 10 milliradian. So this is 0.5 degree, approximately 0.5 degree. Okay, so if our collection angle is less than 0.5 degree, then our detector is bright field detector. If our collection angle of the detector, so remember why I told this Z contrast is means HDF. So this one we collect this Z contrast in STA mode. Okay, so and here the ADF detector, ADF means annular dark field detector. So if our collection angle is between somewhere 10 to 50, so this is the ADF detector, right? If our collection angle is more than that, that means 50 milliradian of the axis, this is the optical axis I am talking about. If our collection, then this kind of detector is known as high angle annular dark field detector. So if we are putting all these things in our if we are collecting all the beams which are which have been scattered by more than 50 milliradian. That means it is an in terms of TEM, this is a very high scattering that we are talking about, because normal scattering is always less than 1 degree or 0.5 degrees. So there we are talking about bright field image, or the scattering will be very elastic scattering, because they will be satisfying the Bragg's diffraction condition. However, if our scattering happens due to inelastic scattering, then those, if we want to collect those scattered, inelastically scattered electron beam and form an image, then we have to put a detector, that is the Hadef detector. Okay, and due to this how we are going to collect this inelastically scattered beam, we can always incident the we can always use the convergent beam we can always use the incident beam in a convergent angle, and then we can scan the entire specimen. So that is why in STA mode, that means scanning transmission electron microscopy mode, we get this Z contrast. And here this is an example, this is an example of alumina substrate. And before going to what kind of material this is, so this Z contrast we generally get or we generally want to use to see different types of heavy metal on a low substrate. So let's say my substrate is here, in this case alumina, and the heavy metal that I am talking about is of uranium, right? If my material is material or particles, let's say small particles are there, if those materials are there, like heavy materials are there on a low substrate, then to view or to get the correct information from those kind of materials, we use this Z contrast. Here all the bright field that you are seeing, these bright fields are the alumina substrate, because alumina has lower Z value, right? And so Z means the average mass I am talking about, right? So here the uranium which I am talking about, or if you say even more than that, uranium, thorium, if I am talking about the heavy metals, then all these darker regions belong to this heavy metals. Why the darker regions? Because this heavy metal will scatter the electron in a direction only the Hadef image can detect, right? Since this is a bright field image, okay, this is a bright field image. When I am talking about all these darker regions belongs to my alumina, which cannot scatter my incident electron beam that to a extremely high angle, right? So to view a heavy metal or a heavy material, not metal, a heavy material on a low average or low atomic mass substrate, we use this Z contrast. And remember, Z contrast is a variant of, I will write it here, it is a variant of mass thickness contrast, right? And here you can see how the Z contrast is helpful for us. So this is one example here, as you can see in the left side, how it is these are the different types of dislocations, by the way. So with the help of, this is a normal TM image, not any kind of contrast acquired. So this is a normal TM. When we do a normal TM, we can see the dislocations are there. From here to here the dislocations are there. However, we cannot say for sure that what different types of material are there. So if we, from normal TM, when we apply this Z contrast, right, when we see the Z contrast, you can see this is this region, it is bright region, and this region, if you can look at this region, this is a darker region, right? And this is the bright region. So when we are seeing this material with Z contrast, then we are able to see whether the mass along the material is constant or not. Since we know that in this material the scientists knew that the masses are not constant, so that is why they went to Z contrast. However, an interesting feature here in the image, you can see all the dislocations which are visible in normal TM, now applying with the Z contrast, they are all gone. That means we cannot, so here this darker region, we cannot say that this belongs to the heavy metal, right? This is also a darker region, so we cannot say that since this is a darker region, this belongs to a heavy metal, right? So this is how we how we can see the dislocation and defects. That is another techniques that we have to see. But yes, the jet contrast, by using the jet contrast we can see that the variation in mass in our sample, right? And similarly, this is an example also that how from a normal TM image, if we apply the jet contrast, what will happen. So here, if you can see, from here to here completely, we are getting some type of atoms, and here this is the bright area, in this area this is a bright area, and this all these area are darker, right? So here we cannot say that we knew in our sample that silicon dioxide is there, germanium is there, and silicon is there. Though three different types of atoms are there in this region which I am highlighting right now, we cannot say that which atom belongs to silicon dioxide, which atom belongs to germanium, and which atom belongs to silicon, until and unless we do a jet contrast. Okay, until and unless we do a jet contrast, we acquire a jet contrast image, we cannot say that which which region belongs to which atom. And now after applying the jet contrast, we can see from here to here this is germanium, and we above that this is silicon dioxide, below this is silicon. So this is how the jet contrast help us interpret the images. Okay, now coming, so there are two types of contrast are there in amplitude the amplitude contrast. One was mass thickness contrast, which we saw, and the next one is the diffraction contrast. So what do you mean by the diffraction contrast? We will see. So we know that some of the planes will be oriented in a certain directions. When our incident electron will be coming and interacting with our specimen, some of the planes will be interacting with them, and the moment these incident electron satisfy the Bragg's condition to these HKL planes, they will be diffracted. So since they will be diffracted, so they will not be coming, they will be going in a certain angle, right? So based on the collection of these rays, or of these diffracted rays, there will be some amount of contrast mechanism associated with our image, and that contrast is known as diffraction contrast. So this is a special form of amplitude contrast where the scattering occurs at special Bragg angle. Okay, so so here what are this diffraction contrast that we are talking about? I'm talking about mostly the, let's say, dynamic contrast, dynamical contrast. Okay, we'll see in the subsequent slide what are the kinematic contrast. Okay, so this diffraction contrast where the scattering occurs at a special Bragg angle. So Bragg angle, if the scattering happens, then what will be the case? Let's say this is my sample, electron is coming, and some of the planes are oriented in a Bragg angle. So instead of and this is my detector, right? So what will happen? Instead of all the electrons are coming directly, some of the electrons, let's say, getting diffracted. Now, though I have imaged my this is my entire sample, right? This is my total sample is there. However, in image plane, what I will get? I will get all let's say I am collecting the diffracted beam right now. I am collecting this diffracted beam. So I will be getting a bright region for the beams which have not scattered, since these beams are all scattered, but in a even though they have been scattered with a Bragg's condition or in a diffracted condition, I will not be able to collect these beams. So they will be so there will be less intensity corresponding to these planes. So due to that, I will be getting contrast, and this kind of contrast is the diffraction contrast. And mass thickness contrast, what was the scattering condition there? In mass thickness contrast, the inelastic, the incoherent scattering happening. Here, the coherent scattering, coherent and elastic scattering happening. Why elastic and coherent scattering? Because the contrast that I am getting, it is due to the planes are satisfying the Bragg's diffraction condition, and due to that, my scattering is taking place. Okay, and since I am talking about diffraction, the electron beam or the electrons must be parallel in order to give sharp diffraction spot. Once I get the sharp diffraction spot, like I have got in this image, or at this spot, then I will be getting a strong diffraction contrast. So until and unless I have the the electron beams are not parallel perfectly or are not completely parallel, then my diffraction spot, those will be some diffuse diffraction spot I will get. So if I am getting a diffuse diffraction spot, then in that case I will not be able to completely distinguish between my bright areas and between my dark area. So in between there will be some kind of gray area will come, which I may or may not able to interpret completely. So this is what is known as the diffraction contrast, and here I can this is a two beam condition. So just a second. Okay, so this is a two beam condition. So two beam condition means what, and why I have told that the diffraction contrast that I am talking about, it is a dynamical. So dynamical diffraction contrast, when I am talking about, that means diffraction, when we talk about, often we generally perceive that my electron beam is coming and it is getting diffracted from one type of plane. Let's say it has diffracted from H1, K1 and L1, right? So we never consider that same diffracted beam also, after diffracting with H1, L1 and K1, H1, K1 and L1, it can again diffract with same Bragg's condition H2, K2 and L2. Similarly, it can also, let's say, Hn, Kn and Ln, right? That means n number of times it can also, the diffracted beam itself can diffract n number of times, right? So, and that means the diffracted electron must be traveling at the Bragg angle to the other Bragg's plane also. That is when so if the, say in this case the Bragg's condition is satisfied, in the subsequent the Bragg's condition is satisfied. So all this time after getting diffracted, the Bragg's angle will be satisfied, and each time it gets diffracted there will be variation in its amplitude, right? So in each time it's the diffracted beam gets diffracted, there will be variation in amplitude, and which will eventually gives us the variation in intensity. And once we say that all this diffraction happens, then our kinematical theory, which we generally assume that the kinematical diffraction, this assumption remains invalid in this case. So that is why in the diffraction, to study this dynamical diffraction contrast, there is the theory called two beam condition, where what we do in two beam condition, we take one strong beam, this is the direct beam, this is the strongest beam in our diffraction pattern, and another beam we tilt our specimen in such a way that one more, that means apart from our diffracted, or apart from our the direct beam, there will be one more strong beam there in our diffracted pattern. We tilt our specimen in such a way that the strongest beam will always be the direct beam, and another let's say stronger beam which will be associated with a diffracted beam, right? So these two will be, and the distance between these two will be defined by the reciprocal lattice vector. So reciprocal lattice vector, if I am talking about, then I am talking about in terms of G. Okay, so this two beam theory, what does it assume this, and so why I have to assume this two beam theory? Because I want to see, after getting diffracted, what is the amplitude variation that is happening in my electron beam. And this two beam theory assumes that, and you can ask that why two beam, why not three, why not four? Let's say why you are only taking one strongest beam and the next strongest beam, that why you are not taking 3, 4 and 5 different beam, let's say out of 15 diffracted spot, because this two beam theory assumes that all the other diffracted beams are very, very weak, and the two beam theory, the relations or the amplitude that we are getting or we are interpreting from this two beam theory, they are not majorly affected by the many beam theory. So there is one many beam theory, but the amplitude that we get from many beam theory is not completely different from the amplitude that we get from two beam theory. So that is why we assume one strongest spot which is related to the direct beam, and the next strong spot or the strong beam which is related to one diffracted beam, right? So this is how we consider the two beam condition. So two beam condition, why do we use? We use this two beam condition to get dynamical diffraction contrast. Here I am writing it again, to get dynamical diffraction contrast in both bright field as well as the dark field image. And in the dark field image, however, since we know that the dark field image contains specific orientation information, okay, why this not any general scattering? Why not general scattering? Because the dark field image specific orientation, when we will get the specific orientation, when there will be diffraction happening in to our material, then only we will be getting the specific orientation. So whichever beam we are not able to collect now in the diffraction contrast, they have been diffracted at a Bragg's angle. So that is why in mass thickness contrast, the contrast we are getting from general scattering information, right? But in the dark field image, if we create a dark field image in two beam condition, then it is always containing some specific orientation information, okay? And to how to set up a two beam condition, we need tilt control to tilt the sample holder. So this is why, if we have if you have remembered, there are different types of sample holder. One will be rotational holder, single tilt holder, double tilt holder, heating cooling holders. So those holder, so out of those, it's a double tilt holder that we use to go to two beam condition. And as a material scientist, we often use a two beam condition to view the diffraction contrast that are taking place in our material. So that is why this double tilt holder is a essential tool for us to collect information from our material. And here how to go, means we can see there are different, this is a diffraction contrast, right? The diffraction pattern. So first we obtain a diffraction pattern related to our material, then we select this this beam, and then we tilt our specimen in such a way that now why you can ask why these two strongest beam will appear, how they will appear. We know that as we rotate our specimen, the reciprocal lattice will also rotate, and as we rotate our specimen we change the orientation of the specimen, the reciprocal lattice will also change its position. So that is how we will be able to always get in this case, let's say two strongest reflection. Similarly here also, this is 0 0 0 2 0 0. Here also we tilt it in such a way that only 0 0 0 and 3 1 bar 1 will be visible. So by rotating our sample in different directions, so that is why double tilt is necessary. Single tilt it is very difficult to achieve the two beam condition. And here you can see this is a bright field image, okay? So this is a bright field image and this is a dark field image. So here we can see completely the complete information, this bright field and dark field, they are completely complementary to each other, and using the two beam condition we can see that there are different areas which will be diffracting from our specimen, okay? And now how the two beam condition is we are able to achieve go to this two beam condition. So let's say first we go, this is the condition where we get our diffracted pattern, the diffraction pattern that we get, that dp. This is our condition. So this is an HKL plane and incident beam. Incident beam is coming. Now let's say we are tilting the incident beam. Either we can tilt our incident beam or we can tilt our sample, right? So so now you can see minus G or plus G. So minus G and plus G are what? These are the, so G is the reciprocal lattice vector, right? So this will be the if I'm at the diffracted the dp, let's say at this point I'm talking about at this position. So this will be my strongest beam, and all other are this one, all will be having less intensity, right? So if that means one will be having strong intensity and another one will be associated with minus G, will be having weak intensity. Now if I rotate my incident beam or if I rotate my sample a little bit, then what will happen? Then you can see this plus G, which was earlier a strong reflection, that means this plus G is associated with the diffraction spot, right? So diffraction spot which is situated at a distance of G. G is the, let's say here I am writing the reciprocal lattice vector, okay? So now this plus G was a strong reflection. So the moment I rotated my incident beam, then the HKL plane is staying as it is. The plus G is now a weak reflection, and the plus 2G is also is a weak reflection. However, the plus 3G is now a strong reflection. So this is how I always remember 0 0 0, this will be the strongest reflection or the strongest spot. You will be able to get that thing. With this 0 0 0, let's say I want to go to a specific plane, or I want to get a strong reflection from a specific plane. So then what I will do, let's say if I am rotating in this direction my beam, I'll be getting 2 strong reflection, and this is the reflection condition, or this is the not reflection, this is the diffraction condition, which will give me the 2 beam which will enable me to go to the 2 beam condition. And similarly from this angle, if I go to let's say left side as imposed here, right, if I am going to, then 0 0 0 will be the one strongest reflection, along with that minus G, which was earlier here, this was the weak one. So when I tilt my beam in the other direction, there is possibility that I will be able to get this minus G. So this is now a strong reflection, and always 0 0 0 will be there present. So this is how we will be always getting this 2 beam condition. So 2 beam condition means the specimen must be tilted to a 2 beam condition. Either you can tilt the specimen, or you can tilt the beam. Generally it is not advised to tilt the beam, because we are having a double tilt holder, so we can always tilt the specimen to go to this 2 beam condition. Okay, and the incident beam must be coherent. Why coherent? Because we are relying on the diffraction spot, and the diffraction spots are we can only get when there will be Bragg's diffraction, right? So that is why it is always coherent. And convergent angle must be very small. Why convergent angle must be very small? Convergent angle small means we are getting parallel beam, and parallel beam means we will be getting sharp diffraction spot, and sharp diffraction spot means we will be getting a good diffraction contrast, right? And one strong diffracted beam and the direct beam, these two are the condition that we go to this 2 beam condition. Okay, and the 2 beam condition, so what do we generally get from this 2 beam condition? Variation of the amplitude with the distance through a perfect crystal. As of now we are assuming that there are no dislocation, no defects associated with our crystal, right? As of now we are saying that this 2 beam condition, there whatever amplitude that is there in our material, by going to this 2 beam condition, it gives us the variation of the amplitude with the distance. Now let's say I am assuming that this phi naught is the amplitude of my direct beam, and this phi g is my amplitude of my the diffracted beam, right? So if I am now if I have to go to this 2, that means I have to somehow get the amplitude, because amplitude will eventually give me intensity, and intensity will give me contrast. So if I want to quantify the amplitude of my, let's say this is my direct beam and one diffracted beam, then I have to go to a certain set of equation. I have to follow a certain set of equation, so that I will be getting I can be able to quantify this amplitude. And this why amplitude I have to get, because the amplitude of each wave changes as the wave progresses through the crystal due to a contribution from the other. That means as my crystal is there, and when the moment I get the direct beam and also a diffracted beam, this direct beam is also getting affected by this diffracted beam, and the diffracted beam is also getting affected by direct beam. So this kind of amplitude variation with the distance, I'll be if I want to quantify, then I can quantify by using a set of equations. Those equations are known as Howie-Whelan equation. Okay, and what do this Howie-Whelan equation signify? They signify that amplitude of each wave changes as the wave progresses through the crystal due to contribution from other. And what are these Howie-Whelan equation? I am just writing it down. D phi naught divided by dz. That means the variation in, so d phi naught by dz is the variation in the diffracted beam amplitude with distance is given by I pi divided by psi 0 phi naught plus I pi by psi g phi g exponential 2 pi I s z. This is one equation. This equation, so if I am saying this is equation 1 signifies the variation of amplitude of the direct beam with respect to the distance. So similarly, another set of equation will also be there, d phi g by dz. It is given by pi divided by Eg phi naught exponential minus 2 pi I s z plus I pi phi g. So these are the two set of equation you have to remember, because there might be a chance that these two equation come in the examination. Okay, so you don't have to completely remember this equation. Once you understand the significance of this different factor, then it will be easy for you to remember. So d phi 0 and phi naught, I have told that these are the amplitude. So here I am writing these are the amplitude. So phi naught is the amplitude corresponding to the direct beam, phi g is the amplitude corresponding to the diffracted beam. So z is the, I am saying z is the, let's say z is the distance. I am writing it here, z is the distance. Okay, now pi and here pi is a constant, we don't have to remember. So here E epsilon 0 and epsilon z, so these are related to terminology. This epsilon g is called as the extinction distance. This epsilon g is known as the extinction distance. So this is the extinction distance corresponding to the diffracted beam, and the epsilon 0 is the extinction distance corresponding to the direct beam. Okay, so these are the two new terms that we have been analyzed, and this extinction distance is the remember this extinction distance is the thickness of the specimen at the first bright fringe. So we'll see what are the bright fringe and what are the thickness of the specimen, how do we get those thickness of the specimen. Okay, and so other term, I think these are the two new terms that we have been introduced. One is the E naught and Eg, and this epsilon naught and epsilon g, and another one is phi naught and phi g. So these two equations are known as Howie-Whelan equation, and they give us the amplitude variation when the wave progresses through the through a crystal. Okay, and with the distance how the amplitude is varied, so they give us this this kind of variation. So these two equation, by solving these two equation, we will be getting our intention, our other, and here there is another term. This term is known as S. S is nothing but the deviation parameter or the excitation error. In the last class we have described those things, the deviation parameter. This is S, you can write it here. S is the deviation parameter. Okay, and eventually though we can say that the diffraction, this Howie-Whelan equation gives us the variation of amplitude, but our aim is to get the intensity, because eventually our detector will detect the intensity of the diffracted electron. So if I am talking about a perfect crystal, then the intensity that due to dynamical diffraction, if the intensity of my diffracted beam which I am talking about, this will be sine square pi t s dash, right, divided by epsilon g s dash square. So this will be my intensity. Okay, and here what do you mean? So here what are the different terminology I am using? So here two new terminology is T. One is T is the, we will know that T is the thickness of the, not T is not the generally we there is a misconception that T is the thickness of the specimen. It always it might not be true. Why? Because this is thickness of the electron traveled through the specimen. Okay, and here there is a new terminology called S dash. S dash is, so here we have seen that the deviation parameter is S, so S dash is nothing but the effective deviation parameter. Okay, so effective deviation parameter, and its value, if I have space somewhere here, okay, its value is I can erase some things. And the effective deviation parameter, if I am talking about, then the effective deviation parameter is given by S square plus 1 by extinction distance square whole half. Okay, earlier the effective so this is the dynamical diffraction contrast that we are talking about. So when we talk about the kinematical diffraction contrast, this deviation parameter will be, this is in kinematic theory. Okay, this is in kinematical theory. So now coming from kinematical theory to the the dynamical theory, there is the addition of this the S and this extinction parameters. Okay, so this is what the intensity of the diffracted beam in two beam condition in Howie-Whelan equation when we are putting all this when we are considering that dynamical diffraction is taking place. Okay, so you have to so this equation you have to remember, and most importantly, what do they signify, these 2 points. Okay, so these 2 points you have to remember for Howie-Whelan equation. Okay, and now we have discussed first we have discussed about the dynamical condition of the dynamical diffraction contrast. Now we will be coming a little bit to the considering all this, that the diffraction is happening only once, and from dynamical diffraction contrast we will be coming to the thickness and bending effect. So, and thickness and bending effect relates to the kinematical diffraction contrast. Okay, remember, whatever we are doing, we are going to only diffraction contrast. Okay, so earlier so this two beam condition is used, and the Howie-Whelan equation is used to quantify the intensity or to quantify the amplitude of the dynamical diffraction contrast. Here we are going to talk about the kinematical diffraction contrast. So kinematical diffraction contrast is is coming due to the thickness and the T effect. T effect means the thickness variation that is happening, and due to the thickness variation there will be diffraction happening, and also S means the bending effect. That means the effective not the effective, the deviation parameter variation, due to that condition also the diffraction contrast occurs. So those we will see. So thickness effect is when the thickness of the specimen is not uniform. As we know that we cannot make a completely uniform material, so the interference between the direct beam and the diffracted beam occurs over different distances. So that is what giving us a thickness effect. And the contrast due to the diffraction contrast arises due to this thickness variation, that is known as the thickness the diffraction contrast due to this thickness effect. Similarly, the bending effect, whenever the orientation of the diffracting planes changes. So in those cases also the diffracting planes will tilt relative to the beam and the contrast change. How it will happen we will see. Let's say so we'll go let's say how the thickness we have seen how the thickness variation has impacted. Now we will also thickness. Okay, okay, so the thickness variation we will see in the next slide. Now let's say we will see some of the bending bending, I think it is there. Okay, so bending is there. We'll first see the thickness effect. So the diffraction that is happening due to the variation in thickness. So we ultimately we also need here the amplitude and subsequently the intensity of this of our diffracted wave, and the intensity of the diffracted wave is given by Ig, same equation that we used in the diffraction condition here, the dynamical diffraction contrast, same equation. Just remember, sine square pi t s divided by extinction distance s square, right? And remember, this is a extremely simplified equation. Okay, and here S is nothing but the deviation parameter. Remember, in dynamical contrast, in dynamical diffraction contrast, we are using S bar or S dash, that is the effective deviation parameter. Here we are only talking about that the diffraction is taking place from one single Bragg's plane, and after getting diffracted, it is directly the beam is getting collected at the detector. So S is the deviation parameter, right? And now if we can see that this Ig and S, if I am talking about Ig versus S, that means a plot of intensity versus the deviation parameter, then I will be getting a curve. That curve is known as rocking curve. Okay, so since that variation, why this is known as the rocking curve? Because if I tilt my sample or let's say oscillate my sample a little bit, then I can, my intensity will also be, let's say initially I'll be getting intensity from let's say this is my highest intensity, then I'll be getting some intensity like this. Initially my intensity I'll be getting like this. Okay, now if I tilt my specimen or I rock my oscillate my specimen, then I will be getting intensity like this. So it will be a varying curve like this, if I am considering that this is my Ig and this is my, let's say, EGS I am talking about. Okay, so this kind of curve is known as a rocking curve. That means when the variation of S can be obtained by oscillating the my crystalline specimen, and all the diffraction contrast that I am talking about, we are talking about the crystalline specimen. Okay, so and this is the equation that you have to remember, which is effectively used in dynamical diffraction condition, right? And now thickness effect, if we have to see, then here we can see that the TM specimen are thin. That means they are thinner than 100 nanometer. More we are talking in a range of 50 nanometer, but their thickness invariably changes. That is why they are also, we can see the bending. So with the amount of thickness that the TM specimens have, we can, even if due to the variation in the thickness, the amount of bending is happening. So that is why the bending effect comes. So like even if we are not doing any kind of bending, we are not putting any mechanical load on the sample, due to the thin specimen, the thickness of the specimen, the variation in the variation in the thickness of the specimen, the bending effect takes place. And planes also bend when lattice defects are introduced. When you introduce a lattice defect, then also this bending effect is taking place. And now if we look at this intensity here, this curve, that you can see the direct beam before interacting with the top surface of the specimen, let's say maximum intensity, and then the curve will be going like sinusoidal curve. Let's say it is a sinusoidal curve which is following. Now the diffracted intensity at the specimen, it will be at 0, because at 0 there will be no diffraction happening. That means at the top surface, so there will be no diffraction happening. So after interacting with the planes, it will be going to maximum as well as coming to down. So this is why, if this is how, if we have a thickness variation here, if you can look at here, that this is a higher thickness and this is a lower thickness material. So this is how, if I am talking about a wedge shaped specimen, the image variation that we will get, somewhere we will be getting the bright image and somewhere we will be getting the dark image and the dark fringes. So these kind of lines we will be getting, and these lines will be the combination of these lines will be called as fringes. Okay, and where the thickness is high, that means less and less number of more electrons are getting diffracted from this region. Let's say from this extreme right end of this wedge shaped specimen, more electrons are getting diffracted. So less intensity, that means less number of electrons will be collected in those areas. So that is why these areas will be will be more darker than as compared to other areas. So that is why the dark fringe you will be able to get, and these kind of fringes if you are getting, that means you are having some effects, your sample is having thickness diffraction contrast. So this is also another example. This is a bright field and dark field example, that these kind of specimen, these kind of image if you get, then you can say that these are due to my thickness variation in my material. It is not an inherent property of my material, rather it is due to the thickness variation. So here you can see some bright fringes are there and some, so these are the dark fringes you can see, and those dark fringes are actually, when we see in a diffracted image, or not diffracted, the dark field imaging, those dark fringes here, this fringe actually has turned like white fringe, right? So this is how we see the fringes in our material. And now that we have talked about this bending effect, that why this bending takes place from these 2 points, we can say that eventually the bending will take place. Now the bending, if the bending has taken place, then let's say my here in this image, if you can see, this is the direct beam which is coming and getting diffracted. So I will be in my, let's say this is my image plane or my detector. Okay, by collecting all these rays I will be getting the final image. So if let's say I am getting all these images and my direct beam is coming and it is getting giving me my diffraction, it is giving me my intensity. So in this place, so I will be getting, let's say, my direct beam which are not interacting or which are not at a Bragg's orientation to all these planes. This is a plane, this is a plane, this is a plane. So now due to bending, what has happened, my Bragg's plane are also little bit inclined from their exact earlier the perfect Bragg's condition. Let's say this is the perfect Bragg condition. Now all these Bragg's planes are inclined. That means they are not situated in a so in a position that they can perfectly diffract. So that is why many beams will be passing through my material, since they are not getting diffracted in a Bragg's diffracted condition. So in that case what will happen, I will be getting intensity all over my sample, all over my image plane. However, whichever beams have been Bragg's diffracted or diffracted according to the Bragg's condition, in this case I was supposed to get a, let's say in this case I was supposed to collect the electron beam. However, since it has been Bragg's diffracted in this direction, so what I will get a dark line. Similar thing also, if my direct beam was supposed to come here and I was supposed to get the beam electron beam, and I was supposed to form an image in this region. However, since it is Bragg's diffracted to some other region, so I will be also getting a dark line or like this. So these kind of dark lines are known as, so these kind of dark lines, when I am talking about, I will be getting these kind of dark lines, they are known as extinction contours. Okay, so extinction contours, so these are the dark region. So the dark region, due to the kinematical diffraction contrast, I am getting this dark region. So same, the intensity is also in this case also given by sine square pi ts divided by epsilon g s square. Okay, and these are the how I will be getting this the image of those. You can see it from the right side. All these due to bending effect, how I can see there are different lines have gone through this and due to bending I can see all these fringes, you can see, right? So all these fringes means there are some planes which have diffracted the beam according to their Bragg's angle, and due to those diffraction I am not able to get all the beams that I was supposed to collect, and due to that these dark lines are coming. Okay, and this is how the diffraction contrast, I generally get the diffraction contrast. So I think Okay, next is the question. So summarizing this all this contrast mechanism, there are two different types of contrast mechanism. One is amplitude contrast, another one is phase contrast. So phase contrast is nothing but when there is a difference in phase, so the contrast will change, because electron waves are eventually dependent on the phase. So now coming to the amplitude contrast. Amplitude contrast is two types of contrast. One is mass thickness contrast, another one is diffraction contrast. Now the diffraction contrast is two types of diffraction contrast. One is kinematical diffraction contrast, which relates to thickness and bending effects. One is dynamical diffraction contrast, which takes into account of the two beam theory, and the amplitude of the two beam theory and the intensity of the two beam theory will be given by Howie-Whelan equation, right? And and in mass thickness contrast, there is a specific type of contrast when we want to see the high resolution imaging technique, when we want to use, that is known as the Z contrast. Okay, so these are the different types of contrast mechanism that we wanted to see. Now going to quickly to the sample specimen. I think which one, just a second. Sample specimen. Okay, so now coming to the sample specimen the specimen preparation for this TM, because that is ultimately this our what type of image that we are going to get, that ultimately is determined by the specimen preparation. So there are two types of specimen preparation. One will be self-supporting specimen, that is the bulk sample that we are going to make, that contains only the specimen, and the specimen resting on a supporting grid. This specimen resting on a supporting grid is generally made to view the powder samples, right? Powder samples. So we disperse those powder samples on a copper grid, carbon which is coated with a carbon film. Then we put those powders, and then we see the specimen. Now coming to the we use different types of polishing mechanism. We use either this perchloric acid as well as the ethanol and methanol of the ethanol or methanol for the polishing of this machine, polishing of our sample and specimen. Then this is the phase diagram that perchloric acetic acid and water phase diagram that we have to take carefully into consideration, so that we will always be in the safe zone. Safe zone is somewhere here, this below this white line, this is the, and this line, this is the safe zone. Okay, going beyond this zone there will be hazardous explosion, so we have to be careful about our combination of the material we are using for polishing. And this is the sample preparation accessories. This is the accessories that we generally use for this is a mechanical punch which we use for to get a 3 mm disc from our material. Okay, so let's say there is a bigger material is there, so we from that bigger material we cut that we first polish that material. Let's say the diameter of your material is somewhat 50 millimeter, but that 50 millimeter material we are not able to put it in the TM sample holder. So that is why from those let's say we first we slice using diamond saw that we saw in the video. We slice the material of the 50 mm diameter using diamond saw, then we mechanically polish that material, and finally when the thickness of that 50 mm material is less than 100 micron, then we 100 nanometer, then we go for this mechanical punch, and here the sample will be there. And once we put this handle towards the right side, all this disc we will be able to extract. And this is a dimpling material, dimpling apparatus. So this is one of the pre-thinning technique that we use. So dimpling is we provide some kind of etchant, and this is a jet orifice, and our specimen will be there, and the specimen will be constantly rotating. So the specimen will be constantly rotating, and once so this etchant will be with time it will be removing the material. So a wedge shaped specimen we can get. So this is a dimpling, that this wheel, you can see this round wheel is there, so it will be rotating in this direction and the specimen will be rotating in from let's say in this direction. Due to that, the wedge shaped specimen is also we are able to get. And then finally, after let's say after doing the getting the 3 disc for metal samples, what we do a method called electropolishing, and that electropolishing we use some electrolyte. So it is based on a trial and error method. So first we optimize the current versus voltage curve, and this electropolishing is associated in the final thinning of the material, okay, when we prepare the samples. And then we have to see that what kind of voltage is so here, as you can see, at low voltage etching happens, at medium voltage polishing happens, and at higher voltage pitting happens. So for to know what is the exact current and voltage combination for our material, we have to do a little bit trial and error method. Then accordingly we have to optimize all the parameters to get the finally thinned specimen. And this here the electrolyte forms a viscous fluid film between the electrolyte and specimen, which this viscous fluid film removes the material slowly, okay. And this is the jet polishing, and when we put our material in the jet polishing, so from both sides we can see a wedge shaped specimen is getting removed. And if you are doing a single side jet polishing, then from one side the wedge shaped specimen will be removed, and this is a twin jet polishing. So this from both the side specimen, this etchant will be, electrolyte will be coming and removing the specimen. And at what voltage, what current we have to carry out this procedure, that we will know by getting this current versus voltage specimen. And this is different for each material. This varies actually from materials to material. And this jet polishing, is the moment this jet polishing completes, since this can change the surface chemistry, this can introduce more surface more damage to your thin specimen. So we have to rapidly extract that material and dip it in and clean it with ethanol or methanol, okay. And this is a ion milling procedure, where for the non-conducting materials, though this ion milling procedure will take place, electropolishing we do it for conducting materials. So the non-conducting materials such as ceramic sample, we do the ion milling procedure, where argon ion comes and this specimen is actually rotating, and then argon ion comes and then it's remove the material from this area. And since the specimen will be rotating continuously, then in that case, in the wedge spaced specimen we will be getting from all the directions, right. And this is a argon thin specimen surface, where we can see the defects earlier. And this is the undamaged crystal, okay. And here this is a argon, here we have used the iodine ion, here we have used the argon ion. As you can see, the beam damage can also happen. And this is a cross section samples preparation. For cross section sample preparation, actually these are useful for thin film specimen. So people who want to view the cross section of the thin film, so it is not possible to let's say some of the silicon wafer, if we are talking about, those are very thin. So if we want to see the TM image of those kind of specimen, then we have to go for this cross section specimen preparation. First we slice those specimen, and then we all these small slices we put inside the spacers. So spacers are some silicon or glass spacer we put, and then we put together, or put all these slices with the help of glue, and then we finally take out the 3 disc, and then 3 disc are subsequently go to 3 disc subsequently go to electropolishing or the dimpling for non-conducting material. And this is an ultra microtomy, which we use exclusively for polymer sample. So here is a knife, and once this the arm rotates, and slowly it rotates, as well as it advances, the step size that we give gives us finally the advancement of this arm. and let's say I am giving 100 micrometer, it should advance once the cutting happens. So this arm goes to the left side by 100 micrometer. So that is how we procure our polymer samples. Okay, because we do this ultra microtomy to polymer samples, because this polymer sample is very much prone to beam damage. So we cannot go to ion milling, or also we cannot go to jet polishing, because it will immediately remove the electrolyte, will immediately etch the sample and do the surface damage. And this is a replication and extraction method for the secondary particles, or the secondary or the extra particles that are present in our bulk sample. And if we want to image the specimen image the surface, or image the features of those particular second phase particles, then we have to do the replication and extraction method. And this is finally the focused ion beam method, where we can, by applying the ion is generally, we do this using gallium ion. And by using the gallium ion, we remove the material, we remove the specimen from the sample. And we view this removal process by using the SEM, the scanning electron microscope, is associated with the FIB, focused ion beam. And it is this fine control of the ion allows incredibly precise TM section. Okay, so that is why this using this FIV method, we are able to get very uniform specimen. So we can avoid the contrast mechanism that are coming. We can minimize the contrast mechanism that are coming from the thickness contrast. Okay, and yes, these are the focused ion beam. Here you can see, first we do a trench cutting in focused ion beam. Now first we do the trench cutting, then there are different types of methodology that are associated with focused ion beam. First we do the trench cutting, that means we remove specimen from to do a focused ion beam. First we deposit, let's say we have identified one area, we deposit the carbon or platinum ion on top of those things, so that there should not be much beam damage to our material. Then we start removing the area to the upper side of the specimen, and the lower side of the specimen. So these are called as the trench cutting. Then slowly we remove the bottom side of this specimen also. So now these two sides are attached. So now after that we remove one side of this specimen. So that is called side cutting. Then we finally do the bottom. Finally we remove the bottom part also, and then finally we take it out with the help of a nano manipulator. Okay, so yeah, this is by using this thing we can take out an extremely small sample. Okay, then after putting all these things, after preparing our samples through electropolishing or through ion milling, we have to clean the specimen surface, so that there should not be any kind of contamination present in our specimen while imaging. Otherwise the interpretation or the information that we will get, it will be in the combination of our specimen as well as the contamination, which we definitely do not want, right? And that is why the plasma cleaner is essentially helpful. And the gases that we use for this plasma cleaner are oxygen, nitrogen and argon. So this is a plasma example of a plasma cleaner, where we put our specimen, and then after doing the final thinning, we put our specimen, and then finally we clean it with the plasma. Okay, and yeah, so now coming back to, what is the time, 7:58. So there are few conceptual questions are there, we'll go through them quickly. Okay, in TEM, so the first question is, in TEM, higher spot size of the beam indicates dash FWHM, lower, higher, or none of the above. So can anyone answer? Higher spot size means?
Lower.
Higher spot size means lower.
Lower field with half inch.
Higher spot size means? It is higher FWHM. FWHM means
Field full with half maximum.
yes, full width half maximum. So higher spot size means my spot is getting bigger and bigger. So if I am getting spots like this, that means full width half maximum is nothing. So full width half maximum is intensity, the half way of my intensity. So what is my the thickness of my peak or of my uh, beam. So if I am getting a higher spot size, that means my spot size is increasing. That means there is much more broadening there. So broadening will be there when my FWHM will be higher. So the lower spot size if I am getting, then the FWHM. So higher spot size means my here in this let's say beam, my broadening is higher. So similarly, this higher spot size relates to my broadening. So the higher spot size indicates that I have higher FWHM, right? So full width half maximum, that means I have the less amount, the less FWHM will be there, it will be better for me. So that is why a higher spot size means I have a higher FWHM. Okay. So this is the next question. Which of the following statement is or are true? The diffraction pattern is not formed on dash. Statement 1 is front focal plane of condenser lens, back focal plane of objective lens, image plane of objective lens. Can anyone answer?
Back focal plane of the objective lens.
Yes, but you have to answer. Okay, so here it is asking that the diffraction pattern is not formed. You have to see this is the not formed. That means the diffraction pattern is formed in back focal plane of the objective lens, right? So the diffraction pattern is formed there. So where it is not formed, it is not formed at the front focal plane of the condenser lens. So it is not formed here, and it is not formed image plane of the objective lens. So that means the correct answer will be statement 1 and statement 3. So that means this is statement 1 and this is statement 3. So C will be the answer, because at the back focal plane of the objective lens the diffraction pattern is formed. Due to that we can project that diffraction pattern there to if we can project the back focal plane of the objective lens to our final image, then we will be getting the diffraction pattern there. So here the diffraction pattern is formed. Here the question is asking that where the diffraction pattern is not formed. Okay. Okay, the next question is the following statement is true or false. The main purpose of cutting extremely thin slices of samples is for better observation of intracellular components instead of extracellular components. True or false? This is related to a biological sample. So why do we cut the thin sample? For TM imaging anyway we need thin sample, but here for the biological purposes, so whether the purpose of cutting thin slices is for observation of intracellular, that means the intracellular, when I say the intracellular means the features within a cell, and the extracellular means the features outside of a cell.
True.
What?
True, sir.
Yeah, this is correct, because we want to, if I am putting my specimen biological sample in the TM, then I want to image or I want to view the intracellular components. So that is why I have to cut the thin slices, and then I have to do the pre-thinning and final thinning, so that I can put my sample in my TM chamber. So okay, the following statement is true or false. If the interplanar spacing in real space is d, the interplanar spacing in reciprocal space will be 1 by d. This is, yes, this is also true. This is one of the easiest question, because that is what the definition of reciprocal lattice is. That is how we have defined our reciprocal lattice. Okay. And the fifth statement is the arrangement of apertures vertically from top to bottom: objective aperture, condenser aperture, SID aperture. So if you have seen the demonstration of the TM in the video, so you can, sorry.
False.
Yes, this is false. In the column, so what will be the first aperture? First aperture is the
Condenser is
condenser aperture. The
condenser.
next aperture is objective aperture. The
Objective.
next aperture is SID aperture.
Saturday aperture.
Okay, so this is how from the TM column from top to bottom they are put. So this is a false statement. So the deviation parameter S is nothing but the distance of the evolved sphere passing through a diffraction spot that is slightly away from the Bragg position in the exact Bragg position. So this is true or false?
True, sir.
Yes, this is true because that is what the definition of so here let's say this is my specimen. This is my specimen and this is where my this is the origin of the reciprocal lattice. Then if my the next reciprocal lattice, let's say instead of here, if it's staying here, then in that case instead of going like this, I have to go like this and this one. This is my G. This is, let's say, 0 0 0. This is some HKL, and if this is G vector, if I am saying that this is K naught, this is KD, then this is S vector. This is the deviation parameter, and vectorially what we have written, KD is equal to K naught plus G plus S. That means KD minus K naught is equal to G plus S. So G is the scattering vector, right? That's what that's how we have defined this deviation parameter. So here dash techniques can be combined with TM to analyze the chemical composition of the sample: atomic force microscopy, Fourier transform infrared spectroscopy, energy dispersive X-ray spectroscopy. So which of the statements are true?
Only three.
Yes. So only energy dispersive X-ray spectroscopy can be associated with the, it can be combined with the TM to analyze the chemical composition of the sample. Right? So when we do the energy dispersive, we can get the information, ADS information, and also we can do the ELS. That means energy, electron energy loss spectroscopy. ELS spectroscopy also we can do. And which of the following electron detectors is commonly used in TEM? Photomultiplier tube, charge coupled device, scintillator, Faraday cup. Which one?
Scintillator.
Which one? I cannot hear that.
C option. Scintillator.
No, scintillator is not used. Currently, we use this one, charge coupled device. Charge coupled device is used in all of the TMs.
SEM only uses scintillator.
SEM we use scintillator. Also in SEM we use Faraday cup.
Faraday cup. Yes. Okay. Smart.
And photomultiplier tube also we use. All the other three we use it in the SEM. So I can write it here, SEM. So if we go to the SEM detector system, these all will be associated with SEM only. Charge coupled device we exclusively use it in the TM. So which of the following is an advantage of cryo TM? So cryo TM means it is not at room temperature. It is very, very less than the room temperature. So cryo temperature. So higher resolution, faster imaging, no sample preparation required, reduced beam damage to sample. Is an advantage of cryo TM. Which one? Okay, so cryo TM means
E option. Reduce beam damage to the sample.
reduced beam damage. That's what saying, right? Or faster imaging.
Reduced beam
Yes,
damage to the
that is the correct answer. The cryo-TM means it will have because cryo-TM we use with less accelerating potential, and cryo-TM are used for preparation or we generally use this cryo-TM to view the biological sample. So that is why we need reduced as minimum beam damage to the sample as possible. So that is where cryo-TM comes in handy. Okay, yeah, the camera constant is given by d L lambda 1 by r and d.
R is L lambda.
Sorry.
L. E option.
So camera constant is
R
given
is
by
equal to L lambda.
L lambda. So the formula is Rd is equal to N
It's equal
lambda.
to
So
L
this
lambda.
L is called as camera length. Be careful about that. In the question they might sometimes give you the camera length, and separately they might give you the wavelength. So you have to multiply that thing to get a camera constant. So combinedly, this is camera
Camera
constant.
constant.
Okay, and this is always constant for a particular TM. And which among the following is a beam sensitive material? Metal, composites, polymer and ceramic. Now, beam sensitive means here I am talking about the TM beam, electron beam, the incident electron beam. Okay, so which one is sensitive? Beam sensitive means we can view the material, but we cannot keep the material, we cannot give a higher exposure time. When we give the higher exposure time, then the beam damage will take place in our sample. So the correct option is polymer, because yes,
Polymers.
polymers, because polymers are having
Low melting.
yes, low melting point, and they are not too much, they are not crystalline sample. So that is why we use this, we use polymer, and when we are using the polymer in TM, we give as minimum exposure time as possible. Okay, the diaphragm or the aperture disc are made up of. So diaphragms are, or the aperture disc are, put it like this. Okay, and this disc are put, whether this is a condenser aperture or objective aperture. Okay, so or SAD aperture also is there. So these three types of aperture are there, and the diaphragm, these aperture are made up of which material? Aluminum, platinum and titanium. Remember, the aperture should be made up of material which should be inert or
Platinum.
non-reactive, because once
Low
it
beam.
starts reacting with your sample, then the result that you will get
That
will
also
be
give the
different.
electron.
Okay, so that is why platinum is the correct answer. To record microstructural images, both objective and SAD aperture are required. It's a true or false? So there are two types of aperture. One will be objective aperture, another one will be SAD aperture. So the
True.
role of this objective aperture is when we want to view
Yes.
images. SAD aperture we insert when we want to see the diffraction pattern. So it will only give us the diffraction pattern. To view the microstructural image, we only need objective aperture. So the statement is false. Okay. Which method can be used for the preparation of polymeric sample or soft TM samples? Jet polishing, ion milling or ultramicrotome? So jet polishing, we use it for metal sample. Predominantly we use it for metal sample or say conductive sample. Okay, ion milling we use for non-conductive or ceramic sample predominantly. Ultramicrotomy we use for this polymeric sample. Why? Because here etching might change the surface structure. Ion milling also beam damage can happen. Okay, so these two things can happen to polymer sample if we do the jet polishing or ion milling. So ultramicrotomy is the way to see the to use the sample preparation for polymer sample. And this is the last question. When using ultramicrotome for sectioning, what is the purpose of using glass knife? To trim the cutting edge of the sample blocks so as to make it flat, to section the specimen into thin slices, to hold the sample blocks. It allows us to monitor the process of sectioning. Why we use the glass knife? It's a simple question. Knife is used for, okay, here this knife is used for
The cutting edge of this.
so the correct answer is to section the specimen into thin slices. So different so knife will be like this and our specimen will be coming. So this is the arm and our knife is like this. So it will be coming and in this direction slowly it will be cutting, and here we will be putting the cup like this, and all these slices will be carried over here. Okay.